Hello, I'm Geeta Kulkarni, working as a staff engineer in the VMware Office of CTO. I have around 16 years of experience in wide range of IT technologies, and my current focus is building data platforms on VMware cloud infrastructure. So I'm going to be talking about how to build a data analytics platform in minutes using deployment blueprints. This is just a quick disclaimer. Let's talk about the goals and objectives. So I'm going to be talking about the implications of managing increasing volumes of data, basically the background of data platforms. You'll also be able to get an understanding of what are the complexities that come with multi-runtime deployments. We will also learn about the solution components and technologies for managing the multi-runtime deployments. Also, there will be a quick demo of how to build a data analytics platform comprising of Kafka, Spark, and Elasticsearch using deployment blueprints in minutes. So in the end, we would talk about the next step. If you want to get started with data platforms, what are the resources? And we'd love to hear from you. We would love to get some feedback from all of you. So let's get started. So, in order to stay competitive, enterprise organizations are making a constant effort to optimize and scale the delivery of their products and services. Data has kind of become very, very critical in achieving this goal. So, as the scale and the number of use cases of data increase, we need data management capabilities that go way beyond the traditional databases. So in addition to data storage, we need applications that support data search, data distribution, data reporting, caching, data enrichment, analytics, and so on and so forth, so that we can manage the data better, especially the large sets of data. So such management capabilities basically require the data application teams to deploy and integrate multiple different data software tools as part of a single data platform. So also with cloud adoption, deployment is now happening on distributed infrastructure, such as Kubernetes, as against how it used to happen earlier, basically having traditional databases being deployed on dedicated hardware. So just to give you an example, a customer might want to stand a data platform, which is comprising of, say, Kafka, which is for data ingest, Spark for data analytics, and Elasticsearch maybe for data search and storage requirements. So if you look at this diagram on the right, this is how your entire stack will look like. So you have your physical infrastructure at the bottom. On top of that, you have your ESXi virtualization platform. Then you have your Kubernetes platform on top of it. Then you have your data platform running on this Kubernetes platform. And eventually you'll have your data applications, which will be running on your data platform. So considering we have multiple different software stacks that form a single data platform, as against how it used to be earlier, where single software was deployed on a dedicated hardware, the deployment automation now needs to cover the installation and configuration of these multiple software runtimes. And also, they need to take care of the placement of these software runtimes across the cloud infrastructure. So when the software runtimes are sized and placed correctly on the infrastructure, that is when we are going to be able to make optimal use of the underlying infrastructure. So when we make optimal use of the underlying infrastructure, that's when we will be able to drive down the deployment and the infrastructure cost. So basically, despite the benefits that are given by the horizontal scaling and deployment agility of each software stack, there are certain challenges that are introduced when we are trying to stand a modern data platform on the cloud infrastructure. Let's have a look at these challenges. Basically, how that basically come with when we are trying to stand this data platform on the cloud infrastructure, and what are the solutions that we have in order to ease the complexity of these deployment challenges so that you are able to stand a modern data platform quickly in minutes rather than in hours or days. So the first thing is, as we said, most data platforms now require deployment of multiple software runtimes, specifically stateful runtimes. which is because we're talking about data. So the question is, how do we stitch together all these software runtimes that are going to form a single data platform? In addition of this, each software runtime is going to have multiple container runtime instances in order to meet the defined scale and resiliency requirement. So that kind of adds to your complexity. So all of this requires numerous steps, which can kind of take hours or days to complete. The second thing is software runtime placement. So data platform implementations require that multiple types and instances of data software runtimes are deployed. How these software runtimes are deployed on the across the server compute and infrastructure matters. Basically, how do I ensure my data platform is resilient? So, for example, in order to ensure node failure resiliency, each software runtime instance should be placed on a different server node. Also, there is also an added incentive to stack together multiple software runtimes so that you are able to better utilize the underlying infrastructure. So, for example, if your placement policies are not defined correctly, there's a possibility that multiple runtime instances of the same software stack could be deployed on the same Kubernetes node, which will cause a single point of failure. So this kind of adds to your deployment complexity. It also adds to the risk. Third important challenge, or the third important point, is resource sizing. How do I size my application? How do I size my data platform? How do I size my Kubernetes cluster? How do I size my underlying ESXi cluster? How do I make sure that I'm making the optimal use of the underlying infrastructure so that I'm able to kind of reduce the infrastructure cost? I'm able to kind of anticipate what is the infrastructure capacity that I would be needing to stand a data platform. So correctly allocating memory and compute resources is essential for the optimal execution of data software runtimes. So tuning parameters such as JVM parameters, JVM memory is one such example. At the same time, minimizing the over allocation of resources requires configuration and tuning of resources, requests and limits at multiple layers of infrastructure. So this kind of adds to the complexity. This creates a new operational complexity, as resource capacity and performance tuning are essential to the modern data platform. The fourth point is implementing data observability. So, how do I configure the observability instrumentation for my runtime metrics so that I can start monitoring my data platform immediately after deployment? So, managing data platform requires monitoring operational state and performance of multiple software runtime stacks, also the underlying server. So, to derive the overall functional status of your data platform, what one needs to do is observability metrics basically will have to be collected from multiple different endpoints. For your server, it would have to be collected for your software runtimes, and they would have to be collected. They would have to be processed, aggregated, and that kind of adds to the complexity of the query on the observability framework portals. So this kind of creates a new complexity when you are trying to configure the observability for your data platform. The last part being maintaining the open source software. So nowadays, open source and the third party softwares are forming serve as a basis for a lot of enterprises. So open source software, how it works is basically you download the open source software tools from the public repositories that are available, and then you use that to deploy your data platform. Now, how does one make sure that the images that you have downloaded are trusted and secure? Also, when there are upgrades and patches that are released for each software tool, how do you ensure that you are keeping a track of the patches and the upgrades that are happening? You basically have to repeat that for each software stack that comprises your data platform. So this creates an operational risk and overhead. So all the deployment challenges that we just spoke about are spread over day one and day two operations. The multiple deployment steps, runtime deployment complexity, estimating the infrastructure capacity beforehand are some of the day one operational challenges. The observability framework instrumentation, or ensuring that you are able to size your resources optimally to make optimal use of your underlying infrastructure. These are some of the day two operational challenges. Now, how do we ensure that we are able to ease the complexity of these challenges? What is the solution? So let's have a look at the solution components now that address these issues we just spoke about. So these are the solution components. So our main goal, as we discussed earlier, is to be able to stand a modern data analytics platform on cloud infrastructure. This modern data platform needs to be optimal and resilient, making optimal use of the underlying infrastructure and thereby reducing the infrastructure cost. Also, secondly, we should be able to auto-configure the observability framework for this data platform so that we can start monitoring the data platform immediately after deployment. So data platform blueprints form the most important building block of this solution. What is a deployment blueprint? So data platform blueprints basically comprise of a single configuration manifest that is used for the deployment of the data platform, comprising of multiple different software stacks and software stacks which are stateful. So these are available as part of as Helm charts in the Bitnami application catalog currently, and they are managed. They are available in the managed repos for version management. These are opinionated blueprints, so you're able to stand an optimal and resilient data platform using them. Also, when it comes to deployment, how you can deploy them is you can do that from command line, or you could do that using a standalone tool, or it could be done as part of the integrated as the Tanzu service. Third thing is the runtime and platform observability. You can use these deployment blueprints, which auto-configure the observability framework for you. If you choose to use Tanzu Observability as your observability solution, you would be able to start monitoring your data platform with the out-of-the-box dashboards that are available in Tanzu Observability. And the last and the most important part is the infrastructure sizing guidelines. The blueprint come in different t-shirt sizes. So say a X t-shirt size of the blueprint would be able to support X amount of in-memory data set. So you would be able to get the recommended underlying infrastructure guidelines. So in order to stand this data platform, what is the underlying Kubernetes cluster size that you need? What I mean by the cluster size is in how many number of Kubernetes worker nodes do you need, and what should be the associated node size. So this is how the deployment lifecycle looks like. The first stage being define, where we define the blueprints and they are made available as Helm charts in the Bitnami application catalog. Second one being deploy, where we will be able to deploy these blueprints either from command line or from kubeapps tool or even from Tanzu mission control. And day two, lifecycle management, which is the run phase, where we would be able to monitor the data platform using the Tanzu observability out of the box dashboards. So in a nutshell, the Helm charts that are available in Bitnami application catalog, they comprise of all of these attributes. As you can see, this image talks about data platform blueprint 2, which is comprising of Kafka, Spark, and Elasticsearch. What this consists of is one, software runtime selections, each software runtime's pod sizing and the number of replicas of each application, pod placement rules, pod security rules, also runtime specific Prometheus sidecar configurations. If you choose to use Tanzu Observability as your observability solution, you'd be able to auto-configure the wavefront collectors and wavefront proxy setup so that you can start monitoring your data platform immediately using the dashboards that are available. And lastly, you would also be able to get what should be the Kubernetes cluster size and the number of nodes of the Kubernetes cluster. So let's have a look at a quick demo now to see how you can build a data analytics platform comprising of Kafka, Spark, and Elasticsearch using the deployment blueprints in minutes. So I'm going to be logging in to the Bitnami application catalog now. Let's first talk about the use case. So for this demo, let's take a use case where a customer wants to start a small size data platform for the analysis of small to medium sized data sets with the ability to process in-memory data set of about 15 GB, to be able to store this process data for at least 5 days, and also support for batch and real-time data ingest of 10 GB per day. Now, this is intended for a group of developers, but it still must be resilient enough to provide reliable data services to these shared group of developers. So the requirement is to deploy a data platform using validated open source blueprint with minimal data configuration changes and also real-time visibility into each software stack runtime for actionable status and performance monitoring. As the main goal is to be able to come up the underlying infrastructure capacity with optimal server and storage footprint to minimize the infrastructure cost. So we are going to, for this use case, we basically have the data platform blueprint 2, which is available in the Bitnami catalog for the containerized deployment of a small data platform comprising of Kafka, Spark, and Elasticsearch. This is a validated and engineered blueprint, which gives you a recommended Kubernetes cluster size as well. And we will be setting up the Tanzu observability framework for this. So these are the solution components. We will first go to the Bitnami community catalog, have a look at the blueprint. The second thing is we will go to Tanzu mission control and have a look at the TKG cluster on which we are going to deploy this data platform. We will be using kubeapps as our front end to the Bitnami application catalog. We will be using this to deploy the data platform using the Helm charts. And we will be using Tanzu observability as our observability solution for monitoring the data platform immediately. Now, let's go ahead and search for the data platform in Bitnami application catalog. So as you can see, this data platform will, in its default configuration, will deploy a Kafka cluster with 3 nodes. It will deploy Elasticsearch with 3 master nodes, 2 data nodes, 2 coordinating nodes, and 1 Kibana node. Additionally, it will also configure Logstash with 2 nodes and Spark cluster with 1 master and 2 worker nodes. So in order to stand this data platform, you need Kubernetes cluster, which is of this size. You need basically a Kubernetes cluster with 1 master node and 3 worker nodes. 3 worker nodes of best effort extra large and master node of best effort small. So let's now go ahead and check the Tanzu mission control to have a look at the cluster. I have already configured this cluster beforehand. This is a cluster which has 3 worker nodes. As you can see, this is of the required configuration that we just saw. Let's now go ahead and try to deploy this chart from kubeapps. You can optionally try to deploy this Helm chart from command line as well. I'm going to do this from the nice form layout that kubeapps offers. You can see you have these toggle buttons to enable the observability framework. Since we're going to enable the observability framework, I'm enabling the metrics exporters for all of these software stacks. And I'm going to enable Tanzu observability. I'm going to configure the cluster name. I'm going to configure the wavefront cluster and also the API token. So I'm going to switch my screen so that the passwords are not visible. And I'm going to deploy this data platform now. So it takes about 2 minutes for the data platform to kind of come up. As you can see, the data platform is now up and running. It has deployed 26 pods and all of them are up and running. The installation notes section here talks about how each of the application that is present in this data platform can be accessed. The application resources section here talks about all the application resources that this Helm chart has deployed. Since Kafka, Spark, and Elasticsearch are stateful applications, they are deployed as stateful sets over here. Then we can, now that the data platform is up and running, we can now log into the Tanzu observability portal and have a look at the out-of-the-box dashboards. You can navigate to the integrations tab in Tanzu observability under data platforms tile. You have these dashboards which are available for different blueprints which are available in Bitnami catalog. I'm going to go and navigate to the data platform blueprint 2. I already have this configured. As you can see, this dashboard has various sections in it. There are the main and the most critical section being the mission control section, which gives you a high level overview of how your data platform is doing. This section talks about health and utilization metrics of the data platform. It also shows you what's the utilization of memory and CPU. One can choose to deep dive into each application stack if one wants to have better look at how each of the application is doing. So you can basically start monitoring your data platform immediately. So in a nutshell, the data platform comprising of Kafka, Spark, and Elasticsearch on a Tanzu Kubernetes grid cluster looks something like this. As you can see, each application pod has been placed on a different Kubernetes node for the best resiliency. Also, the resource sizing of each application's pods has been done optimally in order to make optimal use of the underlying infrastructure. Wavefront collectors and wavefront proxy configurations has been done in order to ensure that we are sending the metrics to the Tanzu observability service so that we can start monitoring our data platform immediately. So basically, these are the key takeaways from the demo that I want to leave you with. You can use the open source data platform blueprints that are available in Bitnami application catalogs. These are available with trusted open source container runtimes. You can quickly and easily deploy a data platform from the KubeApps portal. You would be able to plan your infrastructure capacity before you actually stand your data platform. You'd be able to get the recommended Kubernetes cluster sizing. If you want to enable observability framework, you can do that along with the Tanzu observability framework and also start monitoring your data platform with the out-of-the-box dashboards that are available. So that's it from me. This was the demo. If you want to have a look at the data platform blueprints that are available in Bitnami catalogs, these are the links that are available. We would love to hear feedback from you. So if you have any issues when you are trying to use these blueprints, you can definitely log issues on the GitHub repository. There are certain blog links that are made available here. You could have a look at these blogs to read more or understand more about data platforms and data platform blueprints. Our email IDs are mentioned over here. So if you want to reach out to us, feel free to do so. We would be very happy to receive feedback from you all. So that's it from me today. Thank you for joining me today. Have a great day.